Hey friends, welcome to the YouTube channel All About Electronics. So in this question, we have been given the synchronous digital circuit, and here we have been also given the timing parameters for the given circuit. So basically, here we have been given the setup time and the hold time of the flip-flops, and we have been also given the propagation delay of this flip-flop as well as the combinational circuit. So here, we have been asked to find the maximum clock skew at the second flip-flop, which the circuit can tolerate. And based on that maximum allowable clock skew, we have been asked to find the minimum required clock duration for the given circuit. So let us see that. So here, for the given circuit, the clock skew is defined as delta 2 minus delta 1, where the delta 2 is the time when the second flip-flop is receiving the clock, and the delta 1 is the time when the first flip-flop is receiving the clock. And here, these all are the different timing parameters. So here, this TL is the maximum propagation delay of this combinational logic, and this TS is the minimum propagation delay. Likewise, this TCKQ is the propagation delay of the flip-flop, and this TH and the T setup are the setup time and the hold time of the flip-flops. So in the recent video of the clock skew, we have seen that whenever the clock skew is positive, that means this delta 2 minus delta 1 is positive, then the equation for the minimum required clock duration can be given by this expression. That means this T clock plus T skew should be greater than or equal to this TCKQ plus Tcom plus T setup. Or in other words, this T clock should be greater than or equal to this TCKQ plus Tcom plus T setup minus T skew. So with the positive clock, we have seen that the minimum required clock duration reduces. That means if we have a positive clock skew, then it is possible to operate the circuit at a higher frequency. But at the same time, if we have a positive clock skew, then we might face the hold time violation. And we have seen that to avoid the hold time violation, this condition should get satisfied. That means this TCKQ plus Tcom should be greater than or equal to this T skew plus TH. On the other hand, if we have a negative clock skew, then the minimum required clock duration will increase. But with the negative clock skew, the chances of the hold time violation will reduce. So here in the given question, we have been asked to find the maximum allowable clock skew which circuit can tolerate. And based on that clock skew, we have been asked to find the minimum required clock duration for the circuit. So here, since the clock duration is not yet decided, so first we need to check the condition for the hold time violation. And we know that whenever we have a positive clock skew in the circuit, then and then only the condition for the hold time can get violated. So first, let us check this condition, and based on this condition, let us find the maximum allowable clock skew in the given circuit. So we know that to avoid the hold time violation, this TCKQ plus Tcom, that is the propagation delay of the flip-flop and the combinational logic, should be greater than or equal to this T skew plus TH. So basically, here whatever is the input to the second flip-flop, it should not change up to the whole time of the second flip-flop after the clock age. So here, if both the flip-flops are receiving the clock at the same time, then this condition should be equal to this TCKQ plus Tcom should be greater than or equal to TH. But here, because of the clock skew, this D2 input should remain stable up to the time T skew plus TH. So here, once the first flip-flop receives the clock, then after the time of TCKQ plus Tcom, it will generate the new D2 input. So this new D2 input should only arrive after this time T skew plus TH. And therefore, this condition should get satisfied. So based on this condition, we can find the maximum allowable clock skew for the given circuit. So here, while finding this maximum allowable clock skew, we need to consider the worst case scenario. That means here, we need to consider the minimum propagation delay of the all components. That means here, we will consider this TS for this combinational logic, and here this TCKQ is equal to 1 nanosecond. So further we can write this expression as this 1 nanosecond plus 1 nanosecond should be greater than or equal to this T skew plus TH, and here this whole time is equal to 0.4 nanosecond. So from this we can say that this T skew should be less than or equal to 1.6 nanosecond. Or we can say that the maximum allowable clock skew in the given circuit is equal to 1.6 nanosecond. So based on this clock skew, Now let us find the requirement for the minimum clock duration. So we know that with the positive clock skew, the condition for the minimum required clock duration can be given by this expression. So here, basically to find the minimum required clock duration, we need to consider the time from the first clock edge of the first flip-flop to the next clock edge of the second flip-flop. That means the next clock edge of the second flip-flop should only arrive after the propagation delay of this flip-flop and the combination logic as well as the setup time of the second flip-flop. So here, if we see the time difference between the first clock edge and the next clock edge of the second flip-flop, then that is equal to t clock plus t skew. That means here, this t clock plus t skew should be greater than or equal to this tckq plus tcom plus t setup. Or further, the same can be written like this. So here, while finding this minimum required clock duration, we need to consider the worst case scenario. And for that, here we need to consider the maximum propagation delay of the each component. So here, for the combinational logic, the maximum propagation delay is equal to 2 nanosecond. So with that, if we find the minimum required clock duration, then that is equal to this 1 nanosecond plus 2 nanosecond plus setup time is equal to 0.6 nanosecond minus t skew, that is equal to 1.6 nanosecond. So from this we can say that this t clock should be greater than or equal to 2 nanosecond. That means here the minimum required clock period for the given circuit is equal to 2 nanosecond. So from this we can say that for the given circuit, the maximum clock skew at the second flip-flop which circuit can tolerate is equal to 1.6 nanosecond. And based on that maximum clock skew, the minimum required clock period is equal to 2 nanosecond. And therefore, for the given question, this B is the correct answer.